So if you remember from last time, something about the frequency that we're seeing this system resonate at is off. And so the first place to check is the circuit.
So here is a frequency generator. The first couple steps are to add a loading resistor. It says right here 50 ohms, so that the frequency generator has something to load. And after that, I need to connect my oscilloscope to it, just so I know how much amplitude and make sure the frequency it's telling me is the correct frequency. Okay, so I've got the frequency generator. Right now it's putting out 1K. I don't know what blinking gate red light means, but it seems to be okay for now. I've got the 50 ohm resistor. Across the resistor, I have just the general. Let me move this around. So that's what the purple one is, just to see what the input frequency is. And then coming out of the wave generator, I've got the one of the leads going to ground, and then the other lead going into the output of the previous guy. So in other words, this is my bandpass circuit right here. I've got one lead here, so here's where my bandpass circuit starts, and I've got the second lead here, which is where it ends. And yeah, and so if you look really closely, right here, you should read about 400 millivolts. Now a lot of that is noise. Yeah, it's pretty noisy signal, but that's fine because once we get to the frequency that we're interested in, the noise starts not being as much of a factor. And yeah, so now we can start recording the information in the old-timey way, and we'll see where it gets us. One other thing is I currently have both the polarization coil and the transceiver coil disconnected. I'm trying to see how much of a difference that makes.
So here are the results of that study. Basically, it shows that uh, everything about the circuit likes to resonate around 2200. And so if there's an issue, it's probably not there. It's probably something to do with the coil.
Okay, so if the issue isn't the bandpass filter, then the next place to check is the inductor resistance capacitor circuit right here, also known as LRC or RLC. And so if we plug in the values, I was just testing a couple, but ideally you'd have 18 nanofarads, 700 millihenries, and 310 ohms. So yeah, by themselves, the frequency would be 1400 hertz, but including the larger polarization coil around the inner transceiver coil increases the frequency to the 2100 range. Okay, so just to recap what you see here, in purple are kind of squarey, it's hard to see, but that's the input signal. Blue is what's going into the coil. Yellow is what's coming out of the coil on the other side of the receiver gate. So, in other words, yellow is right around here. It's one of these, this area. And we basically see nothing but noise. And one thing that it could be is that this guy right here is just closed for too long, or it's closed at the wrong time. I'm not sure. So maybe we can mess with the timing of that gate. Okay, so earlier we saw the yellow line being flat, and so what I did is, so if you look at the timings, this guy should be closed at the same time that the signal is coming in. And if that's the case, then everything on this side, if I measure on this side and I measure over here, they should have the same signal, right? Because they're all on the same line. But we were seeing a flat line on one side and we were seeing the curve on the other side. And so what I did is I took a pin for 5 volts and I just directly plugged it into the relay and activated it by hand. And as you can see, now it's making sense. So I'm guessing that relay is not activating, but it's making noise. So there's something we don't understand, or that relay is broken. Okay, so it turns out we just weren't understanding it correctly. If I changed, so the timings were set up so that this side, the yellow side, wasn't connected until out here again. So that explains why we didn't see anything. And if I artificially tell it to stay connected the whole time, then we can see that both sides match. I mean, it doesn't look right but that's because, one's at 50 millivolts and the other one's at 2 volts. But if we change it around, they basically look the same. So that's there. So then what we gotta do is figure out why there's no signal on this side. So as a sanity check, I swapped out the LDOs for basically these batteries that I used in the old system. The idea being that if the LDOs were causing noise because they were attached to wall warts, that you would get less noise on the batteries. But if anything, it's more noisy than before. So I guess that's kind of a good thing. Another sanity check was making sure that the oscilloscope wasn't causing noise. And so what you're seeing here is, the blue and the pink lines are measurements earlier in the circuit. And if they were inputting noise, then changing the attenuation setting on the probe would have reduced that noise later on. And that does not seem to be the case. So we know that that is not the problem. Okay, so another sanity check, just to make sure that this noise wasn't coming through the Arduino, through the USB cable. We were hooked up to a PC, so that was a chance. So here we are with a laptop, which actually works better than the PC somehow, and software-wise, and we are still getting that noise. So we know that this noise is not coming from the walls. So one interesting thing I did is I had the probe set here before the amplifier, and we saw a bunch of noise because we had to magnify it a lot to be able to see anything over there. And then I moved it to the other side of the amplifier where it gets multiplied times 1,000. And now it's super clean. By the way, this ringing that you see is probably the transceiver coil ringing after we changed the switches, the reed switches. But either way, that is way cleaner. So I'm starting to wonder if that noise was just like probe noise or like reading noise. Either way, yeah. And this is starting to look familiar from the last time this worked. So all the testing that we've done on the circuit board so far keeps pointing towards something being off about the resonant frequency of the coil. So I've got this wave generator with a known capacitance here. So we've got the wave generator, the coil, and the capacitor in a loop. And so this should make an LC circuit. The LC circuit will have a fundamental frequency that it likes to resonate at. And so we're going to look for that. And that should tell us, we should be able to work backwards to find the henries of the coil and see if that makes sense. So as you can see, we've got, you can see the purple line is the input frequency, the blue line is the output frequency, and right now we've got a fairly high amplitude for the output frequency because we're close to resonance. If I go away from resonance and test it again, you see that yes, they all got skinnier, but they also shrank down vertically because we're not resonating.
So what you're seeing here is the data plotted out for how much the transceiver coil talks back to us when we put in a certain frequency. And so as you can see, it does have a frequency that likes to resonate at if we give it a certain capacitor, and we can try to fit it using the resonance function, and we see that it gets a peak around there, which then if we know what the fundamental frequency is for this capacitor, we can work backwards to get how many henries, or in other words, how much induction this inductor has, the coil has, the transceiver coil. And when we plot everything in, or plug everything in, we get about 400 and something millihenries. Now, it should be around 700 millihenries, and using the digital voltmeter, we measure around 500 and something. So it's not perfect, but I guess it's within a factor of 10, so I'm going to count that as a win. So I'm fortunate enough that I was able to strike a deal with my coworker. If I brought out his coil winder, his backup coil winder from the box, and tested it and made sure that everything works correctly, he said I could use it for this video. So let's try that out. All right, we got the new coil, and I got some leads attached to it, so let's pop it in. So this right here is connected to the pink tester, is the input signal for the system. It's basically the Arduino sends in a signal to wake up the hydrogen atoms. And as you can see, it's not connected. And yet, the second we unground the coil, it rings, and it just rings forever. And so this is what it looks like right outside the coil, right outside the magnification. And then at the end, where everything's supposed to be, everything's set up so the Arduino can listen to it. And as you can see, it's basically just noise. And by just noise, I mean it's those flat lines means that it's grounding out, that there's way too much, it's way too loud. And that's with the new coil. So as much as I hate to say it, it might be time to break this board up. So the reason I want to break up this board is I was talking to Carl, and he says what might be happening is we've got a magnifier that's really loud, it's 1000 to 1, and we've got a bandpass, and then we got the coil, and that system working together, also with the fact that all the powers are connected to each other, because it's a long strip of power, that's causing a feedback cycle, so that it's basically just ringing and then being magnified, and then just that part's being magnified and just looping in on itself. So I think what I'm going to have to do is I'm going to have to cut it right here, and then have this as a separate thing with its own power supply, which I guess at least we know that we can deal with multiple power supplies. I don't know if there's enough room on my wall for more powers. I guess there is if I unplug the soldering station. And then I gotta find more of those. But that might be the next step, unless I can think of a better way to track this down. I was about to close this out when I noticed something, that my signal definitely it looks a lot cleaner than it used to, but it has that bandwidth that I've seen before when I last got this to work. And so I went and got a magnet, and would you look at that? That little bandwidth is kind of gone, and it just kind of looks like a regular noise pattern there. So I think there might be a signal in the noise.